Today's very short video focuses on one particular Taylor series, one that was developed by Isaac Newton and is named for him. It's called Newton's Binomial series. This turns out to be an extremely important series for a variety of reasons. One of those reasons is that it's very, very useful for calculating roots, things like square root of 3, fifth root of 7, cube root of 13. It's also a series that plays a role in a really efficient way of calculating pi. So we're going to use Newton's binomial series in this video without deriving it. You'll at least do part of that derivation on the worksheet for Wednesday's class. So if you're watching this before that class, just know that you'll actually be able to derive this formula on that worksheet. If you're coming to this video having already been to class on Wednesday, it won't be unfamiliar or sort of out of the blue. You'll know where it comes from. So the binomial series is a Taylor series near x equals 0 for the function f of x equals 1 plus x raised to some constant power alpha. If you find the Taylor polynomial for this function and then extend it to a Taylor series, what you get is that 1 plus x to the alpha is the same as 1 plus alpha x plus alpha times alpha minus 1 over 2 factorial x squared, and so on. I've written down a formula for the nth term, and then I've noted something we'll have to pay close attention to, that the Taylor series converges for all absolute value x less than 1. So we're stuck between minus 1 and 1 when using Newton's binomial series. So as I mentioned in the introduction, this series is really important for getting your calculator to do things like find the square root of 3, right? Lots of calculations that our calculator does we really take for granted. But when you want to know the 7th root of 19, that's not an obvious calculation. Your calculator does it almost instantly. And Newton's binomial series provides one way that we could program a calculator or computer to do those sorts of calculations. So just like we could use Taylor polynomials to do sine x, cosine x, e to the x, we can also use them to do things that we've been plugging into our calculator for years. All right, we're going to see how to manipulate Newton's binomial series to approximate roots to any degree of accuracy that we want. But what we're going to see is that the restriction that absolute value x has to be less than 1 is going to force us to be a little bit clever in how we apply the series. So let's take this square root of 3 as our first example. It might be tempting to do this. Think of the square root of 3 as the square root of 1 plus 2, because the Newton's binomial series, right, has the form 1 plus x inside the parentheses. And I could write that as 1 plus 2 to the 1/2. And then if I wasn't paying attention, I could write this as 1 plus alpha, which is a half, times 2, and so on. But the problem is, here I'm using x equals 2, alpha equals a half. The alpha's fine, but this x equals 2 is a problem. It's outside where the series converges. So this particular way of finding square root of 3 won't work. We have to do something a little more subtle. This will take some getting used to, but here's how we're going to approach it. We're going to rewrite the square root of 3 in a clever way. We're going to multiply by some perfect square on the top and the bottom, so that inside the square root we now have 4 times 3/4. The 4 I'll pull out front of the square root, leaving me with 2 times the square root of 3/4. inside the square root, I can write 3/4 as 1 plus or minus something that is less than 1. I have 1 minus 1/4 now, so this is 2 times 1 minus 1/4 all to the 1/2. And now I've got alpha equals 1/2 and x equal to minus 1/4. And that means I can use the binomial series. So this is 2 times what I would get if I plug in x equals minus 1/4 and alpha equals 1/2 into the series. Since I'm stopping at, well, degree 2, doing 3 terms, I want to be a little careful over here. And note that what I'm getting is an approximation, right? I get an exact value if I take an infinite number of terms, but only an approximation if I stop. So this approximation equals, so that's 2 times 1 minus 1/8 minus 1 over 1/28. So all in all, if I get my calculator out, the square root of 3 will be about 2 times 0.867188, and that's about 1.73438. Now just plugging square root 3 into a calculator gives me 1.73205. So like our previous calculations with Taylor polynomials for sine x and the e to the x, I hope you find this kind of an impressive result. All right, so we've taken something that is not obvious, right, how to find something like the square root of 3 with a calculator, and shown that if we were patient, we could do it, in fact, by hand. And here we have gotten out to within about 2/1000ths of the actual value just by using 3 terms in Newton's binomial series. We've gotten a lot of accuracy, a lot of useful calculation here for a very little bit of work. All right, let's do one more. Let's see how we would go about finding the cube root of 7. All right, let me go ahead and do the cube root of 7 with a calculator. Now let's see how we might have taught the calculator how to get that. We're going to need the same kind of clever algebra to start, but the cube root of 7 we can rewrite, because we can't do cube root of 1 plus 6, right? The 6 would be outside of where the series converges. So what I'm going to do is rewrite that as a perfect cube, in this case 8 times 7 divided by 8. I haven't changed the value, but I have changed the look. That 2 cubed can come out as a 2 in front. So now I'm trying to approximate the cube root of 7/8. And that I can write as 1 minus 1/8 all to the 1/3. So my alpha is 1/3, my x is minus 1/8, and in absolute value that's certainly less than 1, so we're good to go. We can use Newton's binomial series here. So I get this is equal to 2, and now I replace the 1 minus 1/8 to the 1/3 with the series expression. And I'll just go to 3 terms again. So I get 1 plus alpha times x plus alpha times alpha minus 1, that would be a minus 2/3, x squared is minus 1/8 squared all over 2. And again, I'm going to be a little fussy here. That's not an equal sign anymore. It's an approximation because I've stopped after 3 terms. All right, so let's see. I'm going to get 1 minus 1/24. So this is all equal to 2. 1 minus 1/24. Of course, this is all can be done much faster just using your calculator. Approximation is 2 times. So multiplied by 2, I get 1.91319. So this is approximately the cube root of 7. And notice, compared to the calculator version, that's another outstanding result. So we're within about 2 10,000ths, having used just 3 terms in Newton's binomial series. And of course, we can use as many terms as we need to achieve the accuracy that we want. If I needed to go out to 5 decimal places of accuracy, I would try taking one more term. If that didn't do it, I would take another term, and so on. That's going to do it for Newton's binomial series. We'll get some good practice with this and some more practice with Taylor series in general in class on Friday. I'll see you then.